This video is for Stat 310, Handout number 8, Part B, and is going to cover pages 8 through 17 of Handout 8. All right, let's go ahead and get started. Handout 8, Part A, actually considered the overall test for the one-way ANOVA. This part, Part B, is going to cover the multiple comparisons component of doing a one-way ANOVA analysis. So in Part A, we considered the research question of whether or not there was a significant effect due to sleep deprivation on the average number of touches. The data is provided here, and quickly the outcomes from Part A are provided as well. What we learned is that we did have enough evidence to say there was an effect due to sleep deprivation on the average number of touches. In our tests for our individual effects, we discussed the various p-values here and what those meant. These are tests for the individual effects. So what do we look at for multiple comparisons? Or what are the multiple comparisons? Well, multiple comparisons are comparisons that will compare the individual levels to one another. So for example here, if I wanted to compare sleep deprivation level 12 to the sleep deprivation level 18. So how much of a difference do I have in the sleep deprivations between levels 12 and 18? Our standard jump output for that t-test would look like this here. The p-value, if these are two-sided tests, which we normally do for multiple comparisons, the p-value is listed right here at 0.5036. So that p-value is listed right there. Likewise, the p-value for comparing 12 hours to 24 hours of sleep deprivation would be given right below by that p-value there. So we take each of those p-values. So for 12 to 18, we're going to have a p-value of 0.5036. When I compare 12 to 24, we have a p-value of 10.14. When I compare 12 to 30, so both ends of that spectrum, I do have a significant difference here. So the two-sided p-value is less than 0.05. So I do have a statistically significant difference there between 12 hours of sleep deprivation and 30 hours of sleep deprivation. And this is a significant difference in the average number of touches. We can compare 18 to 24. We do not have enough evidence there. That p-value is not small. We can compare 18 to 30. We do have a significant difference there. And then finally, we can compare 24 to 30, and we do have a significant difference there. So when we do our multiple comparisons, we have a lot of comparisons that need to be done. Here we have 6 different comparisons. And just to keep all of these straight, I have identified these as test A, B, C, all the way through F here. So let's just think about what is the test for A getting at. That's 12 to 18. If we want to think about those visually, what that's doing is just looking at, do I have a significant difference between the average at 12 against the average of 18? So that difference that I'm seeing there, is that significant? In other words, is that going to stay away from 0? If I were to do repeated sampling, is that difference going to stay away from 0? Now that difference here is pretty small, pretty insubstantial. So over repeated sampling, I probably cannot say that 12 and 18 are different from one another. And indeed, that's what the p-value is doing up here. It's saying, no, those are not different than one another. If we look at test C, that's comparing 12 to 30, that's a pretty substantial difference. It's a difference of actually more than 3 there. So looking at C, that's going to be 12 hours against 30 hours. So that's going to be that difference there, or represented by that line there. And that line is pretty large compared to the others here. So I have a statistically significant difference between 12 and 30 hours. So that's what those multiple comparisons are about. And we've identified C D and E is significant. All right, so let's consider those in the following. There were a total of 6 multiple comparisons that were done. A concern when doing multiple comparisons is that the overall error rate, often referred to as the Familywize error rate, or the maximum error rate, is not going to be maintained at that 5% level. So what I mean by that is that if I use a 5% level for test A, a 5% level for test B, for C, D, E, and F, there's going to be 6 of those, 6 comparisons that need to be made. And if I use a 5% original error rate, my maximum error rate for my multiple comparisons is going to be 30%. Now our golden rule is to use a 5% error rate. So there is a simple fix that Bonferroni came up with, and that's called Bonferroni's Adjustment. Bonferroni's Adjustment is to simply take the 0.05 and divide that by the number of tests. Here I'm doing 6 tests. So I would use 0.05 divide by 6, which is going to leave a level of 0.0083. Now this is what I want to use to compare my p-value against if I'm using Bonferroni's Adjustment. So here I would be comparing 0.5036 to 0.0083. Not 0.05, but 0.0083. This p-value for test C, which again is that 12 to 30, that was a pretty substantial difference, and it is still significant using the Bonferroni's Adjustment. So the p-value for that analysis is 0.001. That is indeed less than 0.0083. This one here, test E, which is comparing 18 to 30, is significant using Bonferroni's Adjustment. Again, 0.0009 is less than that 0.0083. However, we see that the comparison between 24 and 30 is no longer significant. Now, the nice thing about Bonferroni's Adjustment is that it maintains a maximum error rate of 5%. So that seems like a pretty simple adjustment that we could do. However, it turns out that Bonferroni's Adjustment does not work well in practice. It tends to be overly conservative and does not identify enough of the significant effects. The most common approach to adjusting for the Familywize error rate is to use something called Tukey's Honest Significant Difference, or Tukey's HSD. John Tukey is a famous statistician, and he's the one that invented the box plots. Furthermore, this test has the word honest in it, and I don't know how you could not use a test that has the word honest in it. So he was wise in using that terminology when naming his test. Here's a little bit about the Familywize error rate and how that can be computed. K here, then the exponent here, just represents the number of tests that are considered. And you can see that the Familywize error rate increases pretty quickly as the number of tests increase. Okay, so let's talk about how to get these done inside of JUMP. JUMP has in it Tukey's Honest Significant Difference, and that's the one that we're going to want to use because it is making the appropriate correction to the overall error rate. So JUMP provides 3 different multiple comparison procedures. One's called Students T, Tukey's HSD, and then also Dunnett's. Now, Students T is not to be used, and that is because there is no correction to the overall error rate. So if we go back up here, those individual tests that I was showing you, these are all t-tests here. This is the Student T approach, and we don't want to use this approach because there's no correction to that overall or Familywize error rate. Honest Significant Difference is the one that we're going to want to use, as I've stated, because it makes that appropriate correction to the error rate. Now, Dunnett's procedure should be used when you have a control or a particular control setting in your experiment. So maybe if level 12, was a control, what I might want to do is just compare each of these others against my control. So here I would, in that situation, I would be comparing 18 against my control, 24 against my control, and 30 against my control. I'm not interested in doing all comparisons here. I'm just interested in making comparisons against one other level. So that's going to reduce the number of tests that need to be done. And Dunnett's procedure, is the procedure that is appropriate when in that situation. All right, so I want to go over into Jump here and just show you how to get this output. So let's go ahead and move into Jump. I'm going to select Analyze, Fit Model. Number of touches is my response. Sleep deprivation is going to go in my Construct Model Effects. And then I'm going to click Run up here in the upper corner. We can get those expanded estimates like we were talking about before. Take the zoom off here. So down here I have my analysis of variance with that overall p-value here. And then down below here at the bottom, I have those expanded estimates. With the p-values that we talked about before. The multiple comparison output is up here in the upper right-hand corner. So I'm going to be selecting the red drop-down menu here. And I want to select Tukey's HSD. I end up getting output that's given to me. Lots of output here that we're going to talk through. And then down below, they have what they call the connected letters report. So we'll talk through that now in our handout. So I'm on page 15 of the handout. Here we have Tukey's HSD, and I've identified the output for the various tests. I've actually kind of grayed out some of the other output because it's just repeated. It's all the same information down here below. So we only need to consider these 6 boxes here. And those have been labeled according to what test. So here for A, I would be comparing 12 hours to 18 hours. And what we're getting in here is the 95% confidence intervals. So the standard output here are the 95% confidence intervals. So negative 2.5 up to 1.51. If these confidence intervals catch 0, then they're not statistically different from one another. So if I take 12 hours, the mean for 12 hours, and subtract the mean for 18 hours, and I get 0, that means those two means are equal to one another. So this interval here for test A actually captures 0. So they're not statistically different from one another. Test B, that captures 0. Goes from a positive up to from a negative up to a positive. So that's not significantly different. However, test C does not capture 0. Goes from negative 5.27 up to negative 1 or so. Does not capture 0 there. So those would be different from one another. And then the 18 to 30 are different from one another as well. A little bit about how to compute these confidence intervals. So how are those things computed? I would just need to take if I wanted to do, say, the 12 against the 30 here. So where are they getting the value negative 5.27? What I need to do is take the average for 12, which again is just the overall minus the effect for 12, and then subtract that from the average from 30, which is going to be the overall minus the effect from 30. That difference there is negative 3.25. That's what's being provided here at the top value in each cell, is how different are the two means. So between 12 and 30, they're about 3 apart, 3.25 apart. If I was using the standard t approach, I would want to multiply my standard error by a quantile off the t-distribution. That's what we did on the last handout. But here, I'm not going to use the t-distribution. I don't want to use student t. I want to use Tukey's on a significant difference. So the value that I want to multiply my standard error by is provided here in the jump output, and that's 2.73. And then I simply multiply that by the standard error for the difference. And that quantity is the second value that's provided here in each cell. So we can do that math, negative 3.25 minus 2.73 times the standard error, and I'm going to end up with negative 5.265. Likewise for the upper, instead of doing minus, I do plus there. Now that confidence interval, again, this one's for 12 minus 30 here. This is what this confidence interval looks like. And the interpretation here is provided. So the interpretation here is we're 95% certain that the average number of touches for sleep deprivation level 12 will be reduced by about 1 to 5 number of touches, average number of touches, compared to level 30. And that makes sense. If you're not very deprived of sleep, then you shouldn't be touching the side of that hole as often as if you were using, or excuse me, as often as if you were 30 hours on the sleep deprivation level. So with these comparisons here, in the 95% confidence intervals, what you want to do is actually look for the ones that are in red. So jump indicates the reds are ones that do not contain 0 and would be the significant differences. So here I have differences again between 12 and 30 and 18 and 30. How about the connected letters report? The connected letters report is also provided in JUMP. It's down here on the bottom. Way down here on the bottom. It's giving me a little note that says levels not connected by the same letter are significantly different. So levels, not connected by the same letter are significantly different. So all I need to do here is just look to identify if they share a letter or not. So let's look at 12 versus 18. 12 and 18 both have a B. They share a letter, so they're not different from one another. How about 12 and 24? So looking at level 12 here compared to level 24, yep, they share a letter, also B, so they're not significantly different from one another. 12 and 30, though, if I look at level 12 as a B, level 30 only has an A. So they do not share a letter, so they would be different from one another. Again, I'm going to get exactly the same information as my 95% confidence intervals up above. This is just doing it with just letter indications. How about 18 to 24? 18 and 24 share a B. They're not different from one another. How about 18 to 30? 18 has a letter B. 30 has a level A. So they do not share a letter. They are different from one another. Okay, some final thoughts, kind of putting all of the pieces from Part A and Part B together. In Part A, from the overall test, we just were asking, is there an effect? Is there some type of an effect? And we found out, yes, there was, because we rejected the H0. The conclusion that we made there is we had enough evidence to say that there was an effect. Also in Part A, we looked at the individual, or what we call the main effects. So was there an effect due to 12, different from the overall average? And there was. Was there an effect due to 30, different from the overall average? And there was. So these are just kind of the individual comparisons. The multiple comparisons, that's what we did here in Part B. That's what we considered here, was looking at, is the sleep deprivation different than at 30 different than 12? And the answer to that was yes, it is. Okay, the CI did not capture 0. Or if we want to do the letterings, these levels had different letters. How about 30 and 18? That would be the same thing, yes? Those were different from one another. Again, the confidence interval for that did not capture 0, and they had different letters. None of the other comparisons were statistically significant. So 30, sleep deprivation 30 is statistically different than 12 and 18, but not 24. 12 and 18 were not different from one another. 12 and 24 were not different from one another, and 18 and 24 were not different from one another. Finally, in part C, which will be the next video, the next handout, we'll include some additional considerations. Things like checking the assumptions, investigations of power, things like that. All right, that does it for this handout. Handout 8, Part B. Thank you.